In this session, we are going to discuss about designing of Butterworth filter. First, we will know about what is meant by Butterworth filter. Before discussing Butterworth filter, first we will discuss what is meant by filter. Mainly, it is the requirement of a signal processing person to attenuate the some part of the output signal spectrum and retain other part of the input signal spectrum. So, this is about the filter. So, we'll discuss about Butterworth filter. Uh, the signal processing filter, which is having a flat response in the pass band, can be termed as Butterworth filter and is also called as maximally flat magnitude filter. So, in the year of 1930, the British physicist, the name is Stephen Butterworth, described about Butterworth filter. So, because of that reason, this type of filter is named as a Butterworth filter. There are various types of Butterworth filters are there, such as low pass Butterworth filter and digital Butterworth filter. Now we'll discuss designing of Butterworth filter. See here, the magnitude frequency response of a low pass Butterworth filter is given by the equation h of j omega is equal to 1 divided by inside the bracket we can write 1 plus ohm divided by omega c to the power 2n whole to the power 1 by 2. Let us represent it as a equation number 1. Now this these two parameters will indicate the frequency components of the filter. Let us calculate poles of the Butterworth filter. See, from observing the equation, we can say that there is no zeros term. Only it contains poles because uh, it has only denominator term. Because of that reason, let us find the poles of the Butterworth filter. For that simple thing, I am going to equate the denominator polynomial to the 0. Okay. Uh, so taking square on both sides of equation 1, we will get h of j omega square equal to 1 divided by 1 plus ohm divided by omega c to the power 2n. Square and 1 by 2 get cancels, and equating the denominator of RHS to the 0, we will get the poles. So that is 1 plus this term to the 0. So 1 plus omega divided by omega c to the power 2n equal to 0. Let us assume s equal to j omega. If s equal to j omega, then take square on both sides. S square equal to j square omega square. J square is, we know that is minus 1. Hence it becomes s square equal to minus omega square here. So I will take this square inside the bracket. It becomes, this equation becomes 1 plus omega square divided by omega c square to the power n, that is equal to 0. And we got s square equal to what? Minus omega square. Hence this one I will replace. This one I will replace it as minus s square. Hence this equation becomes minus s square. Take this one towards RHS, it becomes minus 1 minus s square divided by omega c square to the power n equal to minus 1. And then we can simplify as, I will take power as 1 by n. So it becomes n and power term 1 by n get cancels. Minus s square divided by omega c square, that is equal to minus 1 to the power 1 by n. Then further simplification, that is s square equal to omega c square minus 1 to the power 1 by n. Let us multiply the both side by minus 1. So this minus term get cancelled. S square equal to minus omega c square multiplied by minus 1 to the power 1 by n. And let us take square root on both sides. Hence we got s equal to square root of minus omega c square minus 1 to the power 1 by n. So I will separate the terms. That is square root of minus 1 I have taken separately. Omega c square and square, this one get cancels and left with omega c, and minus 1 to the power 1 by n. Square root of minus 1 to the power 1 by n, we can write it as minus 1 to the power 1 by 2n. J square equal to minus 1, we know, correct? So that one I'm going to substitute here. S equal to square root of minus 1 is what? J square omega c, the remaining term as it is. Next, s equal to square and square root get cancels. S equal to j omega c minus 1 to the power 1 by 2n. And here I am going to assume that minus 1 equal to e to the power j multiplied by 2k plus 1 multiplied by 5. If you simplify this term, you are getting the answer as minus 1. Similarly, I am going to assume as j equal to e to the power j pi by 2. E to the power j pi by 2 means cos of pi by 2 plus j sin pi by 2. Cos of pi by 2 is what? 0 plus j sin of pi by 2 is 1. Hence, we are getting j. Similarly, if you simplify this term, we are getting the answer as minus 1. So, these two things I am going to substitute in this equation. Hence, this equation becomes s equal to j is what? E to the power j pi by 2 omega c as it is minus 1. Minus 1 we taken as a e to the power j 2k plus 1 multiplied by 5 and left with what? 1 divided by 2l. Hence, let us take the power term commons. Hence, s equal to omega c equal to e to the power j, e to the power j 2k plus 1, and here I will take pi outside and j outside, left with what? 1. So multiplied by pi by 2n. Hence, this term I am going to, the term of e, the power term of e, I am going to represent it as theta. So this is theta. If it is theta, s equal to what? Omega c multiplied by e to the power j theta. E to the power j theta means where theta is what? The term. This is term is called as theta. Where theta is what? 2k multiplied by pi by 2n. So 2 get cancels, pi k by n. Next plus n get cancels, pi by 2. Hence pi divided by 2n. So the theta value is this much, where the value of k varies from 0 to 2n minus 1. In short, we are writing s equal to omega c angle theta, phase angle theta. Hence, where k is any value, so sk equal to omega c theta. So our equation gives, equation number 3 gives the poles of the Butterworth filter, which has equal number of poles on the left hand side as well as right hand side. But a filter is said to be stable. A filter is said to be stable. We have to consider only left hand side poles. So we have to consider only left hand side poles. So we calculated poles of the filter. Let us calculate order of the filter for the Butterworth. Order is indicated as notation n, order of the filter, order of the Butterworth filter. So from the magnitude frequency response of the Butterworth filter, we can write node of h of j omega square equal to 1 divided by 1 plus omega by omega c to the power 2n. Before calculating order of the filter, let us discuss the frequencies and attenuations which are present in the Butterworth filters from this diagram. See, this is the maximally flat. We can say, as I told, Butterworth filter is having maximally flat pass band. So flat pass band is there, and uh, so the this horizontal axis represents what the frequency component, and the vertical axis represents magnitude. Uh, Now, where if the value of omega, the frequency component, is equal to omega p. Omega p stands for passband p. P stands for, suffix p stands for passband edge. Omega is the frequency component. Hence, omega p is indicated as passband edge frequency, where omega c stands for cutoff frequency. Omega s stop band edge frequency. Similarly, if the frequency component, if the frequency value is omega is equal to omega p, and the corresponding gain is called as, attenuation is called as passband attenuation, where P stands for passband, A stands for attenuation. The corresponding attenuation is called as passband attenuation. Similarly, if the frequency value omega is equal to omega equal to omega s, then the corresponding attenuation is called as stop band attenuations. Okay. Now, same thing I am going to express in equations. If the frequency value, this frequency value lies between 0 to omega p. If this frequency value lies between 0 to omega p, nothing but what we are getting? We are getting pass band. We are getting this one. If the frequency value omega lies between 0 to omega p, this is what? Pass band. So that is represented as the value lies between, magnitude lies between h of j omega lies between AP and 1. So this lies between AP and 1. This amount of magnitude is present when omega is equal to omega lies between 0 to omega p. Similarly, second case, if the frequency value is omega s, greater than omega s, nothing but what? Then then this magnitude, then this magnitude lies between 0 and as, 0 and as, where AP stands for pass band attenuation and AS stands for stop band attenuation. Omega P is pass band edge frequency, omega S is stop band edge frequency. Let's see the calculate the order of the filter. As per the diagram, at omega equal to omega P, then what we are writing? The magnitude is equal to what? AP. From the diagram we can observe. Hence AP equal to what? 1 divided by, it is the equation, magnitude frequency response equations. Hence AP equal to what? 1 divided by 1 plus omega equal to omega P divided by omega C to the power 2n whole to the power 1 by 2. This term I will take towards the LHS. Nothing but before that I will take the square on both sides. A square P is equal to, squaring means this square root get cancels. Then take towards the LHS. Left with what? 1 plus omega P divided by omega C to the power 2n. And this is present in the numerator. If you take towards the RHS, it becomes denominator. So hence 1 divided by AP square. Now for the simplification, I will take 1 towards RHS. Hence omega P divided by omega C to the power 2n equal to 1 by AP square minus 1. Similarly, if you calculate stop band attenuation at frequency component is omega equal to omega s, we are having the magnitude is as AS, stop band attenuation. So similarly, we can write omega s divided by omega C to the power 2n equal to 1 divided by A square minus 1. Let us take the ratio of equation 4 and 5. 4 and 5, that's nothing but dividing equation 5 divided by 4, then we are getting omega s by omega C to the power 2n divided by omega P divided by omega C to the power 2n. So the power term 2n I have taken common for this ratio. Then what is left? 1 by A square minus 1 divided by 1 by AP square minus 1. Now further simplification, omega C and omega C get cancels. Omega C and omega C get cancels. Left with what? Omega S divided by omega P to the power 2n. That is equal to 1 by A square minus 1 divided by 1 by AP square minus 1. So let us take, because what we are calculating order of the filter. Order of the filter is represented as n. This we have to express this equation in terms of n. N is present at the power term. So because of that reason, I will apply the logarithm log. I will take log on both sides, then it becomes 2n log of omega s by omega p, then that is equal to log of 1 by A square minus 1 divided by 1 by AP square minus 1. Then except n, the remaining term I will take towards the RHS, then this equation becomes n equal to, this becomes as it is, divided by 2 log of omega s by omega p. So this is the equation used for calculating order of the Butterworth filter. The point we have to observe here, all these values AS and AP are not expressed in terms of decibels. So this equation is holds good if the values are not given in dB. We have to use this equation for calculating order of the filter if the values are not expressed in terms of decibels. If the values are expressed in terms of decibels, then how to calculate order of the filter? For that equation is, see here. If AP and S, passband attenuation and stopband attenuations, are given in terms of decibel, then how to express AP in dB? That is nothing but 20 log of AP. If you express AP in terms of decibel, that is nothing but multiplied by 20 log AP. So for the simplification, 20 log AP we can write 10 log of AP square. 10 log of AP square. Then as per the logarithm concepts, 10 log of AP square, that is equal to AP in dB. Next, I will take 10 towards the RHS side. So AP by 10. So log of AP square equal to AP divided by 10 in dB. Next, 1 by 10 nothing but we can write 0.1 AP in dB. Similarly, take NT log on both sides. then we are getting AP square equal to 20 log means 10 to the power minus 10 to the power 0.1 AP in dB. Next, 1 by, let us take the reciprocal, 1 by AP square equal to, it becomes 10 to the power minus 0.1 AP in dB. Let us represent it as a equation 7. Okay. Similarly, we can write for the stop and attenuation 1 by A square equal to 10 to the power minus 0.1 AS in dB. So equation 7 and equation 8 substitute in the previous equation, that is equation number 6. We will get order of the Butterworth filter in terms of decibel as n equal to log of, it is what, 1 by A square is there. 1 by A square is nothing but 10 to the power minus 0.1 AS in dB minus 1 divided by 1 by AP square is there. 1 by AP square is replaced by 10 to the power minus 0.1 AP in dB minus 1 whole divided by 2 log of omega s by omega b, omega p. So one point we have to remember, the filter, this is the equation used for calculating order of the Butterworth filter. So fine. Next, one point we have to remember, after the calculation of the order of the filter order must be rounded up to the next larger integer value. So for example, if we, after the calculating the order of the filter, if we got the answer like this, n equal to 2.3, this is not the order of the filter. Order should be what? Integer value. So because of that reason, we are round offing to the next nearest value, that is n equal to 3. So the answer becomes, order of the filter becomes 3. Next is about calculation of uh, cutoff frequency. We will calculate the cutoff frequency of the Butterworth filter. So from the previous equations, equation 4 and 5, we can write omega p by omega c to the power 2n, that is equal to 1 by ap square minus 1 is there. This one already we discussed. Similarly, omega s by omega c to the power 2n, that is given as 1 by a square minus 1. So by from using these two equations, we can calculate the cutoff frequency of the Butterworth filter as, see here, I will take power term as 1 by 2n, then it becomes, this term get cancels, left with what? Omega p divided by omega c equal to 1 by ap square minus 1 whole to the power 1 by 2n. Similarly, I will apply for this one, then we will get omega s divided by omega c equal to 1 by a square minus 1 to the power 1 by 2n. So if cutoff frequency, in order to design the filter, to meet the cutoff frequency for the passband edge frequency, then we will consider this equation. In order to meet, if cutoff frequency to meet passband edge frequency, you have to consider this equation. Then that is indicated as omega cp, nothing but cutoff, c stands for cutoff frequency, p stands for passband edge frequency. Hence omega cp equal to omega p. See, rearrange the terms. We want this one correct, omega c. Hence, omega c equal to, this will take towards RHS and this term will take towards LHS. It becomes omega p divided by 1 by ap square minus 1 whole to the power 1 by 2n. This is the cutoff frequency in order to meet passband edge frequency. Similarly, see, one more point we have to remember. This is the equation for when the values are not given. These values are not given in dB. Okay. Similarly, for this equation, if find the cutoff frequency to meet stop and edge frequency, then we can write. Okay. Before that, if you express this cutoff frequency to meet passband edge frequency in terms of decibel, nothing but 1 by ap square is replaced by 10 to the power minus 0.1 ap in dB minus 1 whole to the power 1 by 2n. Okay. Similarly, if cutoff frequency meets the stop and edge frequency, then we can write omega cs equal to omega s divided by 1 by a square minus 1 whole to the power 1 by 2n. This is the equation holds good for when the values are not given in decibel. If values are expressed in terms of decibel, then 1 by a square is replaced by omega cs equal to omega s divided by 10 to the power minus 0.1 as in dB minus 1 whole power 1 by 2n. Fine. We calculated two cutoff frequencies to meet passband edge frequency and stop band edge frequency. But overall, actual cutoff frequency of the Butterworth filter is nothing but it is the average of omega Cp and omega Cs. Hence, the cutoff frequency of Butterworth filter is calculated as omega C equal to omega Cp plus omega Cs divided by 2, taking the average of these two things. This is about the equation for finding the Butterworth filter. The last term parameter for Butterworth filter is that is about system function of Butterworth filter. How to calculate system function of Butterworth filter. This is the equation for calculating system function. HA of S equal to omega C is nothing but cutoff frequency to the power n, order of the filter, divided by S minus S1 complex conjugate of S minus S1, S minus S2, so on. Or we can also express in short, HA of S equal to 1 divided by S minus Sk. See, LHP stands for what? Left hand poles. LHP stands for what? Left hand poles. The value of K varies from 0 to 2n minus 1. Already I told, a filter is said to be stable. We have to consider left side poles. Because of that reason, I have taken LHP, left hand side poles. And one more shortcut method for finding the system function is that is representing the system function in terms of uh, polynomial form. This is factorial form. This is polynomial form. For that, equation is omega c to the power n divided by s to the power n plus vn minus 1 multiplied by s to the power n minus 1 plus so on v1 into s plus v0. Okay, this is about polynomial form. Okay, for the factorial form, this table you have to remember. uh, Even also if you are not remembering this table, easily we can calculate by using poles and so, but it will take the time. Because of that reason, in order to avoid time consumptions, better to remember this table. If you are expressing this what system function of Butterworth filter in factorial form, this table at least up to 6 we have to remember, then it is easy to do the calculations. So if this table indicates about what, if you are expressing Butterworth filter system function in factored form, nothing but if order of the filter n equal to 1 is there, then h of s equal to 1 divided by s plus 1. If order of the filter 2 is there, n equal to 2 is there, then system function of the Butterworth filter is 1 divided by s square plus 1.4142 s plus 1, so on, n equal to 3, we are getting this answer. 4, this 5, this 6, this. Likewise we have to calculate the system function. Okay, and coming to table for uh, polynomial form, for that also one table is there. It is the very easiest table. See here, if order of the filter is 1 is there, then of course only 1. Then if order of the filter is 2 is there, 1 point nothing but I am talking about these values. Here, as per this equation, I am talking about these values. If order of the filter is 1, if order of the filter is 1, then what we're getting, 1 divided by, see, as per this equation, if order of the filter is 1, substitute here n equal to 1, hence this is always 1, 1 divided by s to the power 1 plus 1 minus 1 b naught. B naught is nothing but always b naught is 1, hence what we're getting, s plus 1, of course. Similarly, go for if n equal to 2, s square plus 2 minus 1, it is b1 to the s into s to the power 2 minus 1, that is 1 plus b1s, that plus b naught, nothing but s square plus b1s plus b naught we are getting. So what are the values of b1 and b naught? So for that reason, this table we have to remember. For n equal to 2, b1 is 1.4142 and this is 1. Always remember, in the above table, bn nothing but order of the filter. If order of the filter is 2, then nothing but b2 equal to what, b naught equal to what, 1. So if order of the filter is 2, so b2 is what, 1. Similarly, if order of the filter is 3, b3 is what, 1. If order of the filter is 4, b4 is what, 1. Next, if order of the filter is 5, b5 is what, 1. If order of the filter is 6, b6 is what, 1. If order of the filter is 7, b7 is what, 1. If order of the filter is 8, b8 is what, 1. Here, b8 is 1. Nothing but bn equal to p naught equal to 1. Always, irrespective of order of the filter. And very simple here. See, observe the values. 2.613. And this is equal to what? B1 equal to B3. Next, if order of the filter is 5, then B1 equal to V3. Sorry, V1 equal to first value and this one, and these two are same. Next, coming to here, n equal to 6, 3.864 is equal to previous value. Then 7.46, this is equal to this one, and this is 9.141. Similarly, n equal to 7, simply we can remember this one by using this idea, 4.494, and this is same. 10.103, this is same. 14.606, this is same. Similarly, last value n equal to 8, 5.186, same. 13.138, sorry, this is 13.138. Next, 21.848, 21.848. Next, 25.691. So this is about the Butterworth filter. By using all these concepts, nothing but the system function, order of the filter, pose, and we have to calculate, we have to design the low pass Butterworth filter.